The material we're about to look at involves often evaluating limits. We'll be looking at what are called improper integrals. Those are integrals to infinity or integrals to a discontinuity. And to go to either of those places, you approach them with a limit. And then we'll spend a good chunk of time looking at series, which are infinite sums. And there you're adding up forever. And to figure out what that sum is involves taking a limit to infinity. So we'll be looking at limits. And as you recall from Calc 1, sometimes limits have a form that when you look at them, you can't tell what the limit is. And in Calc 1, we did some algebra manipulation in order to get into a form that we could interpret. But sometimes that's not always possible. So we have something that's very useful called L'Hopital's rule that handles exactly that sort of situation. So let's look at what it says here. We're looking at two functions that at the point we're interested in, they're both 0. So f at a and g at a are both 0. And we're looking at this limit here as we approach a of their ratio. So if you tried to just plug a into that to figure out the limit, you'd have 0 over 0, which doesn't tell us anything, right? 0 over 0 doesn't exist. So what really matters is the rate at which they're approaching 0. So what L'Hopital's rule says is that limit is equal to this other limit here that's the ratio of their derivatives. So instead of looking at the limit of that original ratio, we look at the limit of the ratio of their derivatives. Now there's some criteria here before you can just apply L'Hopital's rule. It says that there has to be some interval around a, that point that you're interested in, where both functions are differentiable. And pretty much everything we've ever looked at in calculus would fit the bill, because you can make that interval as tiny as you like. So the only way that a function fails that is if it has infinitely many points where it's not differentiable around a. And we don't really see functions like that in here, right? We have stuff that'll have points somewhere where it's not differentiable, but not infinitely many on a finite interval. So that part about f and g both being differentiable on an interval around a, not a problem. Obviously, it has to be differentiable at a, because we're going to take that derivative. And then same thing here. It also says that the derivative of g can't be 0 on that interval. Well, think about it again. You can take that interval as small as you like. So the only way a function could continually be 0 around a, no matter how small an interval, is if it was 0 at infinitely many points around a. And really the only function we see like that is the function that's just plain old 0, which we wouldn't be looking at the constant 0 function anyways. So really those restrictions don't stop us from using L'Hopital's rule. So pretty much with the stuff we deal with, if it's 0 over 0, then we're going to be able to use L'Hopital's rule. The last thing here is that we have to be a little bit careful. It says assuming the limit on the right exists. So if we apply this in the new expression, the limit doesn't exist, that doesn't necessarily mean the original limit doesn't exist. So long as you get something here that does exist, then that's what the original limit is. So let's look at an example so you can see how we use L'Hopital's rule. So this was, if you recall from Calc 1, this was a central limit, an important limit we used in Calc 1, so much so that I think it got a theorem name. But in Calc 1, we had to go through quite a bit of geometry to prove this was true. Because the problem is, if you just try and plug 0 in, sine of 0 is 0. X at 0 obviously is 0. So what you have, it's not equal to 0 over 0, but I like to say it's of the form 0 over 0. What I mean by that is it's something headed to 0 over something headed to 0. So it has that form, and that's exactly the form that L'Hopital's rule requires, right? You want both your functions at a to be 0. And that's exactly what we have. So let's apply L'Hopital's rule. So it says that that limit should be equal to this new limit, which is the derivatives, the ratio of their derivatives. So derivative of sine is cosine, derivative of x is 1. Now, we're going to be using a lot of theorems coming up in the future, and I want us to get in the habit of justifying everything we do. So whenever you use L'Hopital's rule, I'd like you to quote it, and you can just say by LHR there. Now look at this. This is no longer indeterminate. As x approaches 0, cosine approaches 1. So that limit is just 1, which is the limit that we determined in Calc 1 for that. Now I do want to emphasize something here. You may wonder, well, why did we go through all that trouble in Calc 1? If you recall, we set up a unit circle and did some sandwich theorem with the area of a sector versus an area of a triangle, and it was very involved geometric proof. Why didn't we just introduce you to L'Hopital's rule and then do it that way? Well, you have to remember why we were interested in this limit in Calc 1. This limit arose in the process of trying to figure out what the derivative of sine was. Well, to do L'Hopital's rule, you have to take the derivative of sine. So you can't use the derivative of sine to try and derive the derivative of sine. So we were stuck. We really did have to figure this out geometrically to even get to the point of knowing that the derivative of sine is cosine. Even though we already knew this limit from Calc 1, I think it's a nice first example that limit is just 1. Now, in the statement of L'Hopital's rule, we're looking at things of this form, 0 over 0. And there's a proof for this in the text if you want to look at the proof. What is harder to prove, but we're going to use it, is you can also extend L'Hopital's rule to situations where top and bottom are both going to infinity or negative infinity. So ratios of infinities are also what we call indeterminate. You can't tell just by looking. Infinity over infinity might be 1, might be 2, might be infinity, might be 0. We'll use L'Hopital's rule on those as well, and we'll look at that next.